I'm going to step away for 30 seconds. I'll be right back.
Okay, we'll start when you get back. Okay, welcome everybody. Let's get started. So today we are joined by the team of Keivan Stassun and Marina Kounkel from Vanderbilt University. So I'll let Keivan introduce Marina. I'll introduce Keivan just briefly. So I'll go over some of the things he's done just in the last 5 years. He has a long list of accolades, but I was looking up his papers on Harvard Abstracts today. And his most recent paper has 1 citation, but the next paper after that, which was also published this year, has already 42 citations. And then after that, his papers have respectively 247, 303, 245, 79, and 187 citations. And those are all just in the last 5 years. So it's really an impressive number of citations. There's obviously a lot of work. It's a lot of interest, it's high impact work. So Keivan has worked on things like the test input catalogs and Gaia parallax offsets and empirical stellar radii. So we'll hear hopefully about a lot of those exciting results today. But I also just want to mention that while writing all of those papers, he was also a co-investigator of the TESS mission, the chair of the executive committee of SDSS. He recently launched a Center for Autism and Innovation. He was awarded the HHMI Professor Award with a healthy bonus along with it. He was voted Mentor of the Year by AAS. He received a White House Presidential Award and was also on the Decadal Steering Committee, which we heard about last week from Fiona. So he's obviously very active, and we're very lucky to be hearing from Keivan and Marina today. Take it away.
Thanks, Jim, and thanks for the update on my publication stats. I'm not as up on them as you are. As you all will see, well, first of all, thank you for the opportunity to join you. I'm sorry couldn't join you in person, but you all understand the current situation. Appreciate your accommodation. As you'll see in this presentation, this is really a vehicle for Marina's really incredible work in the last few years, sort of, I think, sort of changing our paradigm for understanding the structure of local stellar populations. So, one of the great privileges of working at a place like Vanderbilt and doing this kind of work is getting to recruit and work with fantastic postdocs like Marina Kounkel. Marina was an undergraduate, it was a graduate student with Lee Hartman at the University of Michigan. And they did a first postdoc with Kevin Covey and really getting involved in Sloan Digital Sky Survey work with Kevin, and now brings that expertise to our team here at Vanderbilt. As you'll see, you'll hear all about Marina's, I think, really important work in the second half of this. So we're going to do this as a tag team, and I'll do the first half to kind of set the stage, and then Marina will take over. The big picture point of all this is to demonstrate what is possible when we bring together the torrents of data that we now have available across the domains of ultra-precise light curve data from tests, for example, large-scale spectroscopy from surveys like SDSS and others, astrometry en masse, like we're getting from Gaia. The combination of those things is really transforming our understanding of fundamental stellar astrophysics and our understanding of local stellar populations. To get to that story, I'm going to start by taking a step way back and talking about individual stellar benchmark systems, specifically eclipsing binaries, share with you some examples of really interesting stellar astrophysics that we can learn when we understand stellar benchmark systems, individual stellar benchmark systems in great detail, and then let that take us into this new generation of being able to do precision stellar astrophysics en masse. Okay, that's where we're going. So Marina, so let me remind you that for centuries, eclipsing binaries have been gold standards for our understanding of the fundamental properties of stars. Eclipsing binaries have the benefit that for the two stars in an eclipsing binary, you can accurately and empirically measure all of the fundamental stellar properties, masses, radii, temperatures, luminosities. You can get these properties with a really good analysis and with really good data. You can get these properties to the of order 1% level. And you can do that without needing to know the distance to the system, right? Which, before the Gaia era was always a limiting factor. Next slide. And so here I'm going to show you a couple of examples of what's possible with really careful sort of boutique analyses of individual eclipsing binary star systems. Most of my work in this area has been with young eclipsing binary star systems in particular. Here I'm showing you a young pre-main sequence eclipsing binary star system, and you see the masses and the radii that we're able to derive from a combined light curve and radial velocity analysis. And you see the precision that is achievable there of order 1%. In fact, there are no fundamental stellar properties of pre-main sequence stars that we know more accurately than the masses and radii of these two stars. And what's involved is, if you see in the light curves there, you see, of course, you see the eclipses, the dips, but you also see a kind of a sinusoidal pattern imprinted on top, and that's because the stars are spotted, and we see that modulation as the stars rotate. The spots on the stars that cause that modulation also cause also imprint a kind of noise on the radial velocities that you measure, and so that would limit your ability to accurately measure the masses of the stars. But we're able to model all of that together. We can account for the effect of the spots on the light curve, simultaneously correct the radial velocity measurements in order to get the most robust measures of the masses and the radii. Okay, advance, please, Marina. Here's another example where, in this case, we have a system of two young brown dwarfs whose masses and radii we can directly measure because they mutually eclipse. Here we have two substellar objects, one with a mass of about 60 Jupiter masses, the other with a mass of about 40 Jupiter masses. You'll notice the radii are quite large despite those very small masses, and that's because indeed this is a very, very young system in the Orion Nebula cluster, a nominal age of about 1 million years. And so these are still very early in their contraction, and so still quite large. If we place the two brown dwarfs in this system on an HR diagram, you see at the right, and I'm showing a fiducial 1 million year isochrone, you see that the lower mass brown dwarf, the 39 Jupiter mass brown dwarf, basically sits where you would expect it to sit, at least in the context of this particular model isochrone. The red bar on the 1 million year isochrone there for the 39 Jupiter mass object. That red bar shows you with the uncertainties where you would expect the blue dot to be, and it's basically where you expect it to be. The higher mass brown dwarf, on the other hand, is way off to the right. It's at a much cooler temperature than you would expect for its higher mass of about 60 Jupiter masses. If you compare that blue dot, the upper blue dot, to the upper red bar on the isochrone, you'll see that it's at about the right luminosity. It's about the luminosity that you would expect for its age, but its temperature is much, much too cool. So we decided to kind of deep dive into the system to try to understand the physics of what's going on there. Clearly something interesting happening. So advance, please, Marina. And one of the things that we followed up with was a careful measurement of the chromospheric activity on the two brown dwarfs in this eclipsing binary star system, represented now in the diagram with their H-alpha emission luminosities. And you see that the more massive brown dwarf, the one that's strange in its position in the HR diagram, has about an order of magnitude stronger H-alpha emission, presumably an order of magnitude stronger chromospheric activity. Next slide. So we followed up the system even more. I like this image at the top. It shows you we can actually detect the H-alpha emission, the chromospheric H-alpha emission from the brown dwarfs on either side of the whopping nebular emission from the Orion H2 region as the brown dwarfs Doppler shift red and blue into the wings of the nebular emission. Anyway, so we can measure that H-alpha emission directly for the two brown dwarfs. We were also able to separately measure their rotation rates. And so the bottom line is that the more massive brown dwarf, the strange one, is spinning much, much more rapidly. It's more chromospherically active, as measured by the H-alpha emission, than its lower mass counterpart. And so that got us thinking, next slide, that perhaps there's a relationship in general between chromospheric activity, presumably magnetic activity driven by stellar rotation, as we know is the case in solar type stars. Perhaps there's a general relationship between chromospheric activity and this sort of corruption of the expected stellar properties, in particular the temperatures and the radii. And so this motivated us to assemble a larger sample of low mass stars in eclipsing binary systems and well-measured ones in the field. And you see that there is a relationship. It's noisy, but statistically significant, where the stronger the chromospheric activity, presumably magnetically and rotationally driven chromospheric activity, the stronger that is, the more suppressed the surface temperature becomes, and simultaneously, the larger the radius becomes. And that temperature suppression and radius inflation work together in a way that the Stefan Boltzmann luminosity basically is preserved, okay? So we were able to find this general relationship, and then advance, please, Marina. Coming back to the eclipsing brown dwarf system that motivated all of that to begin with, if we now apply that relationship between chromospheric activity and temperature suppression and radius inflation, if we apply that as a correction, if you will, to the observed properties of the higher mass brown dwarf in that system, you see that we can effectively infer where that higher mass brown dwarf would be in the HR diagram were it not magnetically and chromospherically active. It would have been in the right in the expected place on the HR diagram. To be clear, that higher mass brown dwarf is in the wrong place in the HR diagram. That's where we actually observe it to be. But we can now attribute that strangeness to a really interesting physical effect of surface magnetism, presumably rotationally driven, that actually alters these fundamental properties, temperatures and radii. Okay, that was all to say that with these stellar benchmark systems where we can accurately measure these fundamental properties, we not only are able to accurately characterize the properties of the stars, but in cases like this, we're actually able to elucidate some really interesting stellar astrophysics in the process. And that was just from one system, 2 objects in one system. Next slide, Marina. So, but eclipsing binaries can also be used. I mentioned at the beginning that part of what has made them so valuable in the past is that we did not need to know the distance to them in order to measure these fundamental properties. But we can turn that around. And since we're able to measure those properties so accurately without needing to know the distance, we can turn that around and use them as a kind of standard candle. You may be familiar with the fact that the Hipparcos satellite, or I should say infamously, got the distance to the Pleiades wrong, as demonstrated by distance measurements from a number of other techniques. A few years ago, Trevor David and collaborators used an eclipsing binary system in the Pleiades to, in a sense, as a distance benchmark to yet again show that the Hipparcos distance was wrong, and that the longer distance inferred from other methods was the correct one. But so this gives us an opportunity to really develop eclipsing binaries as standard candles now as we enter the Gaia era, right? Hipparcos got the distance to at least 1 star cluster wrong. We want to make sure that we can benchmark the Gaia parallaxes as well. So advance, please. What I'm showing you here is, as of the Gaia DR2 release, a characterization, a measurement of the global systematic offset in the Gaia parallaxes as determined by a sample of about 150 benchmark eclipsing binaries that Willie Torres and I assembled from the literature, okay? 150 eclipsing binary star systems, standard candles, and as you can see here, at least as of Gaia DR2, we were able to, at the level of some tens of micro arc seconds, quantify the global offset in the Gaia parallaxes being about 80 micro arc seconds. That's actually not a negative statement. That's actually quite a positive statement, because the Gaia team in their data release documentation recognized that there was likely to be a systematic offset of up to 100 micro arc seconds. So what we basically were able to show with these eclipsing binary standard candles is that they were quite right, that the systematic error budget was indeed within 100 micro arc seconds. We were, however, able to quantify it and also demonstrate the sense in which that offset, that systematic offset existed. Okay, so now that's what we're able to do with 150 eclipsing binaries. And as of the turn of the previous decade, this is where we were when it came to sort of precision stellar astrophysics with these kinds of benchmark systems, okay? Thanks to Hipparcos, right? There was no Gaia 10 years ago. Thanks to Hipparcos, we had of order 100,000 good stellar parallaxes right within the solar, largely within the solar neighborhood. I just told you that Willie Torres and I had assembled of order 100 eclipsing binaries that provided sort of benchmark, of order a couple percent accuracy, empirical stellar masses and radii, okay, about 100, of order 100. In terms of astroseismology, that provides, detailed determination of stellar structure and other stellar properties. we didn't even have Kepler in 2010 yet, right? And so the boom that has occurred in astroseismology since then hadn't yet occurred. And you could basically count on one hand the number of stars for which you could do that kind of ultra precise characterization. In a minute, I'll show you, where we are 10 years later, but this is where we were 10 years ago. Okay, next slide. And so the era that we're entering now, that we have entered, is one in which we have this confluence, as I said at the beginning, of industrial scale spectroscopy. We have all sky, ultra precise light curves. We have extremely precise astrometric measurements, parallaxes, and proper motions, and all within this very, very large footprint, right? So by the time Gaia is done, we will have, essentially for this half of the galaxy, we will have these precision measurements for millions of order a billion stars. And so what can we do? Advance, please. I want to introduce to you an idea that I've been referring to as pseudo interferometry. All right. So I just showed you how with eclipsing binaries, we can essentially directly measure radii of stars through eclipses. Now you're familiar with interferometry, right? And here's an image of an actual interferometric measurement of a nearby bright star, Antares. This is a tour de force measurement of the radius of a star, as you see, with a precision sub-milli arcsecond precision measurement of the radius of a star. Okay, that's actual interferometry. What I want to show you is that we can now actually do this on a very, very large scale and with comparable precision with this pseudo interferometric technique. So advance, please. And the trick is essentially to invert the Stefan-Boltzmann relation. If I can measure the bolometric flux at Earth of a star, and I have a good measurement of its temperature, such as from a good spectrum from some industrial scale spectroscopic mission, now I have a measurement of the star's angular radius, right? So advance, please. This is how we can now, thanks to all sky catalogs, panchromatic from the UV to the mid-IR, directly measure bolometric fluxes of stars on a large scale. Here I'm showing you spectral energy distributions for two random stars. You see a stellar atmosphere model, but you see the individual flux measurements from Galax in the UV to Sloan Digital Sky Survey in the optical to 2MASS in the near IR to WISE in the mid IR. We can literally just kind of string these flux measurements together, get a bolometric flux for the star. Advance, please. And we can do that with really good precision. Those actually weren't two random stars. These are two stars that have been measured with actual interferometry. And what you can see is a comparison of the angular radii directly measured with actual interferometry compared with the angular radii we infer with the pseudo interferometric method. And you see the agreement is fantastically good at the micro arcsecond level. Advance, please. Applying that method now to a large sample of planet hosting stars, you see here from this work, indeed, the typical precision we achieve on the angular radii is like 2 micro arcseconds, okay? At least as of Gaia DR1, what you can see is when we bring in the Gaia parallaxes, we can turn those angular radii into actual radii. You see that we can achieve of order 1–2% precision on the stellar radii. As of Gaia DR1, we could do that out to distances of, say, 100 parsecs. With Gaia DR1, we were still limited actually by the precision of the parallaxes. With Gaia DR2 and beyond, you see we extend that of order couple percent precision on the stellar radii out to distances of a kiloparsec and beyond. Okay, next slide. And now if one of these stars whose radius we have measured pseudo interferometrically happens to have a planet orbiting it and that transits it, we can relate the transit parameters to quantities that we can express as related to a mean stellar density. And so now if I have a stellar radius that I've measured pseudo-interferometrically and I have a mean stellar density from a planet transit, now I have a stellar mass. And then it can also turn the equations around and get the radii and masses for the planets. We can do that all entirely empirically with these measurements. Next slide. And so as of Gaia DR1, we're able to determine stellar masses in this way, in this entirely empirical way, with a precision of a few percent out to maybe 50 parsecs. With Gaia DR2 and beyond, again, we achieve that kind of precision of a few percent on the masses out to approaching a kiloparsec. Okay, so that gives you a sense of the volume of space that we can access with this approach with precision stellar radii and masses. Next slide. So that's measuring a stellar radius pseudo-interferometrically and then inferring its mass because it's orbited by a planet. With eclipsing binaries, we're basically doing the same thing, except the star is orbited by another star. What about singleton stars, not orbited by another star, not orbited or transited in any way by a planet? Well, it turns out we can infer the surface gravities of individual stars using these surface granulation that is imprinted in the excess noise, if you will, of an ultra-precise light curve, such as from Kepler or TESS. This was demonstrated by my former student, Fabien Bastien, and we've now applied that to large samples of stars. Next slide. And this is just to show you that the surface gravity that we infer on the y-axis from this light flickering, this granulation flickering method, when we compare that to the surface gravity that is measured astroseismically for an astroseismic benchmark sample on the x-axis, you see that the agreement is fantastically good. We can infer, and then if you have a stellar metallicity measurement, say from a nice spectrum, there are opacity effects that also come to bear, kind of second order. Anyway, we can infer stellar surface gravities with a precision of 0.05 dex approximately, with a good light curve and with a metallicity measurement. Okay, so that's a pretty accurate surface gravity. And next slide. If I take my pseudo-interferometrically measured radius and now my surface gravity measurement from a light curve from granulation flicker, this is a single star. It's not orbited by anything or transited by anything. Now I can infer its mass from its radius and its gravity. And advance, please. When we consider the number of stars that are accessible to Gaia, for which the necessary measurements are available to do bolometric fluxes and to do the pseudo-interferometric method, these are the kinds of numbers of stars that are accessible for precision stellar radii on the one hand and masses on the other. And I'll remind you that at the beginning of the story, I was telling you about two stars and individual eclipsing binary systems that, took one or 2 years of my person hours. Now we can do this on a much larger sort of industrial scale, thanks to the confluence of these massive and sort of ultra precise data sets. Next slide. And so I'll end now my part of the presentation to say, this is where we're at as we enter the 2020s. Compare the numbers of stars for which these different kinds of precision measurements are possible. And I always think it's sort of unfortunate to represent this with exponents because it loses some of the punch. But you see this enormous increase in the availability of parallaxes thanks to Gaia. But now look at what that means for precision fundamental stellar properties like masses and radii. It's explosive growth. And I haven't even really talked about astroseismology and that whole industry that has exploded as a result as well. So I'm going to hand it over to Marina now to pick up the story. I've been really focusing on these sort of direct observables and measurables of fundamental stellar properties. Marina is going to pick it up now to talk about stellar ages, and when we put all that together, what that means for our understanding of local stellar populations and star forming history of the galaxy. But before Marina takes it over, maybe we'll see, Jim, if there are any questions specifically pertaining to the first part.
Okay, thanks, Keivan. So there is a question from Dimitri. He says, I missed how you infer surface gravity from granulation flicker in the light curves. How precise is that method?
Yeah, so what we measure, Dimitri, is an excess noise in a light curve. Say I have a Kepler light curve, and I know how much noise to expect just from photon noise for the brightness of that star. We can measure an excess noise in the light curve, and we now know that that excess noise is actually a signal. It's a signal of the fact that the surface of the star, we don't resolve the surface of the star, obviously, but the surface of the star is not smooth. It is variegated because of the surface granulation, and that surface granulation has a time scale and an amplitude, and that's what we see in this excess noise. We call it flicker. And using an astroseismic sample for which the stellar surface gravities were known independently, we were able to show that the amplitude of that granulation-driven excess noise is directly correlated with the surface gravity of the star. This is actually a known effect. We know that surface gravity is the primary determinant of the surface convection properties and amplitude, and that's what we see in the granulation. And we can infer the stellar surface gravities with a precision of about 0.05 dex in the best cases with that method.
Okay,
and no, it does not separately depend on stellar activity, although in extremely active stars, depending on the time scale for the activity, it can just in practice become more difficult to extract the stellar granulation signal.
Okay, so there's also a question from Carl Grillmayer. He wants to know if the problem with the Hipparcos distances to the Pleiades was ever identified.
I'm not going to touch that with somebody. I don't think so. I think not definitively. In fact, I'm not sure that the Hipparcos team ever actually formally acknowledged that there was a problem.
Okay, and maybe last question for this segment. Shri wants to know, has the Wilson-Bapu effect been calibrated?
Oh, Shri, come on. What is the Wilson-Bapu effect? Oh, that's the gravity effect on some line. I'm sorry, I don't remember. What is the Wilson-Bapu effect?
Shri, can you unmute?
Yeah, no, this is the chromospheric reversal you see in the calcium HNK. And I wanted to know, and since that was the primary method for quite some time.
And it's a gravity indicator, right?
Well, it's usually used for distance. It's been a long time. I mean, the last time I thought about it was 40 years ago. So anyway, I thought, since has this been revisited now that you have these things? Not
by me, as I just confessed. I couldn't exactly remember what it was. Maybe we should look at that. I thought the Wilson-Bapu effect was a gravity indicator, but
no, the luminosity of the reversal line in the depth of the calcium HNK related to something, I don't know, and that's how you get the distance. It's a luminosity effect.
Okay. Let's look at it. You want to look at it together?
Yeah, it'll be fun.
Sure. Okay, Marina, tell us about ages and stellar strings, please.
As Keivan has summarized, in the last decade, we have significantly improved our understanding, or at the very least, our ability to measure various stellar properties. But another property that is very difficult to estimate for all the stars en masse are their ages, because all the main sequence stars look very similar to one another for the most part. Historically, the stars that have been easiest to identify their age were the stars that are found in the young star forming regions, the pre-main sequence stars. And in particularly, if stars still have protoplanetary disks, they are highly redundant. Therefore, they were fairly straightforward to find with various infrared surveys. But after a star loses its protoplanetary disk, it becomes a naked photosphere and it looks like just any other field star. Still, from analyzing various star-forming regions, we have been able to figure out some patterns of how precisely stars form and what are these regions like. First of all, that stars rarely tend to form in a complete isolation. They tend to form together with at least some other stars within the same region, from anywhere from a few hundred to several thousands of stars. These star-forming regions tend to be fairly dispersed. They have an intrinsic size of a few tens to a few hundreds of parsecs in diameter. People tend to say that most stars form in clusters, but kind of depends on how you define a cluster. And when looking at these star-forming regions, some do have very massive clusters such as Orion Nebula, but in reality, a lot of stars also can be rather dispersed in more diffuse environments. And these star-forming regions also tend to be dynamically cold with velocity dispersion of only a few kilometers per second, and less than a few kilometers per second in some of the less massive ones. And so with that comes a question, well, how long do these regions are actually going to stay together? How long would we be able to look at these regions and still recognize a massive ablation that once was forming there? Will it be a few tens of million years, 20, 50, 100? And by that logic, if we were to look at 10, 20, 50, 100 million year old open clusters, should we expect these clusters to be fully isolated? Or should we expect to find an extended halo of stars that have formed alongside these clusters in an extended star-forming region that currently persist as a moving group? Well, finding moving groups is nothing new in the solar neighborhood. In the past, we have known of approximately about a dozen of moving groups within a volume of space of 100 parsecs. Very few of them have been known beyond that for a fairly good reason. Hipparchus didn't really have good sensitivity or resolution to give accurate distances, give accurate proper motions beyond 100 parsecs. And you kind of do need proper motions in order to find them. But now with Gaia, we can extend this boundary just a bit further out. And so performing hierarchical clustering of the Gaia data, we have been able to identify a very large number of moving groups that are found in a similar volume of space that have very similar proper motions. Within a kiloparsec, there's a total of approximately 3,000 moving groups, 1,000 moving groups of approximately 300,000 stars within them. Extending this boundary out further to 3 kiloparsecs, we have almost 1 million stars within 8,000 different populations. And they fill out a much larger volume than the previously known open clusters that are shown in yellow in the same volume space. So we have quite a different spatial coverage. You can pretty much look anywhere in the sky and find a star that belongs to a moving group now. And what's nice about these moving groups is that presumably all the stars within them have formed at the same time. Therefore, it's possible to estimate their ages through isochron fitting. And for the most part, these moving groups tend to follow isochrons quite nicely. You have the youngest populations in red, still having a very sizable low mass pre-main sequence population, but eventually they start evolving down and down onto the main sequence. And then after approximately 100 million years, you have all of the older populations, all the high mass stars within them start to dying off, and you have a nice turn off that is evolving over time. And so we can take all of these populations and we can color code them all by the age in which that they have, from the red being the youngest, purple being the oldest. And we can look at not at just where these moving groups are in the plane of the sky, which is the top panel, but we can also look at them as the galactic longitude as a function of parallax, as a function of various velocity components. But this is a very busy diagram. It's very hard to tell what is happening here. So for the time being, let's just look at the youngest stars with an age younger than around 30 million years. And what becomes apparent looking at this middle panel in particular is that an individual moving group, an individual young population, can stay coherent for several dozen degrees in the plane of sky, or approximately 200 parsecs in physical units on average. And this coherence, this string-like form, isn't just a chance alignment. You see all of these strings be coherent in all of the dimensions, including radial velocities. And because radial velocities are still not quite as, we don't have quite as many of them as we do have proper motions with Gaia, and Gaia's radial velocities are not quite as precise. They haven't been used in clustering, but the fact that you see the same coherence in radial velocities shows that these populations are indeed very real, and that we're seeing just one large structure. So this is what's happening on the youngest end. What if we were to look at something that's a bit older, let's say something closer to 1 gigayear? Well, here it's starting to look a bit messier. You have many more compact moving groups that don't have extended structures around them. But with some poking and prodding at the data, it's possible to find these extended strings of stars, even at these fairly advanced ages. So if we were to separate the sample explicitly into stars that are young and the stars that are old, and to segregate them into these extended strings of stars versus a more compact, more isolated moving groups that don't have anything else around them, we find that at the young ages, you have a lot of strings, and they tend to be fairly sharply defined in the proper motion space, with only a handful of more isolated groups being found at these ages. On the other hand, at the older ages, almost everything that is clusterable is part of these more isolated moving groups, with only a handful of fairly diffuse strings still hanging about. Looking at it in a different way, looking at the number of stars within a population as a function of age, strings are ubiquitous at the youngest ages, but they tend to go away after approximately 100 million years. On the other hand, these compact, these isolated clusters, cluster-like groups, they tend to come into prominence at around 300 million years. And looking at the number of stars in a given population as a function of age. At the youngest ages, a population can have pretty much any number of stars you want. You can have anywhere from a few hundred stars to several thousands of stars. But at the oldest ages, it's fairly rare for you to have more than a few dozen stars still clusterable together. And most likely the populations that are still detectable at these very old ages as coherent have probably started somewhere over here. They probably have started out very massive when they were forming. So with this in mind, what is the origin of this extended structure? What is the origin of these strings? Well, it's unlikely to be caused by the tidal stretching of the previously compact clusters, because then you would expect everything to start compact and then slowly incrementally stretch out, whereas we see something that's entirely different. You start out very large to begin with. And more importantly, many of these strings don't even necessarily have a compact cluster at their center. Some of them might have, for example, you have Orion Nebula within the Orion complex, but some of them can have a more or less uniform stellar density. Rather, it is likely that this structure is primordial, that we know that stars from giant molecular clouds. Clouds themselves tend to be rather filamentary, and where we have gas, you're going to start forming stars. So it stands to reason that these populations are going to retain the morphology of the clouds from which they have formed. And these stellar populations are slowly dissolving over time. They are spreading out and slightly stretching out from originally rather elongated dimensions. Eventually, only the densest and most cluster-like parts of these populations is going to remain. Everything else is going to be completely dissolved into the field of the galaxy. But some of the most massive ones will be able to survive for a considerable length of time. Now, so before we were looking at everything in 2D, now let's switch our thinking to 3D and then trace all of these strings along their spine and place them in the context of the entire galaxy. Well, the sun here is at the center. Galactic center is to the right. Here we have the Sagittarius spiral arm. Here we have the local arm. Here we have the Perseus arm. And right now we're looking at relatively young strings, younger than 50 million years. And you can see that their orientation is not precisely random, that they tend to be oriented in parallel to one another, perpendicular to whatever spiral arm they're found next to. And this is quite interesting because since all of these stars formed from molecular clouds, this suggests some sort of a dominant formation mechanism for the clouds that form these strings. And looking at other galaxies for possible analogs, even though we don't have quite the same resolution when we look at those galaxies, looking at the molecular gas maps, here we have a spiral arm, and here we have these feathers that protrude away perpendicularly relative to the spiral arm. And so again, wherever we have gas, you're going to start forming stars. So it is possible that these feathers also occur here in our own galaxies, and they may be responsible for the formation of the molecular clouds from which we observe these populations to have formed from. But as great as hierarchical clustering is, as great as is our ability to identify all of these moving groups, we are not going to be able to identify all of the members that have formed within these populations, because in order to use clustering, you kind of assume that everything is found in a similar volume of space, everything is moving with a very similar velocity. And some stars are very eager to leave their home nests, even at fairly young ages, and some do so much more violently than other stars. In the past, there have been several dozens of young runaways that have been identified that are moving with speeds of in excess of 10, 20, or 30 kilometers per second relative to the cluster from which they have escaped from. Most of these stars have been found in the Orion Nebula for a few relatively good reasons. First of all, Orion Nebula is a very well-studied cluster. So we have very pristine catalogs of its members. We have a lot of confirmations for many different stars that these stars that we think are members are indeed quite young. And so if we don't want to rely on the kinematics of stars to confirm their membership, we can use these external age catalogs. And then when we see if a particular star is moving in a peculiar fashion, then the star is likely a runaway. And even if we didn't have these pristine membership catalogs, identifying members of Orion is fairly straightforward, if right now, at least in the age of Gaia, because when we make an HR diagram, we have all of these low mass pre-main sequence stars being pretty obviously separate from some more evolved field stars, such as the main sequence stars or the red giants. You might have some confusion between them, but for the most part, pre-main sequence stars are pretty obvious. But this is only if you are looking at just one particular region that you know how far away it is, you know its general properties. What if you wanted to find pre-main sequence stars across the entire sky? Well, it becomes a bit trickier because unlike just having a more or less single age population that is clearly younger than the field, you have a more smooth gradient as you mix in different ages together. So you might have 1 million-year-old stars and 10 million-year-old stars and 30 million-year-old stars all slowly blending together to the main sequence. So you no longer have a clear separation between them. Furthermore, if you want to look at more distant populations, then extinction is rather an issue. And so you have all of these horrible red giants scattered into the parameter space of lovely young pre-main sequence stars. So if you had an infinite amount of time and infinite patience, you can look at each and every one of these stars individually and determine and convince yourselves if a particular star is likely to be young or not. But we don't have infinite amount of time. But we can train a computer to perform a distinction between them. Now that we do have this very large catalog of cluster structures for which we actually know the ages of all these stars, we can train a neural network to make a distinction. Well, is the star more similar to the young pre-main sequence stars in the cluster catalog, or is it more likely to be a field star? So we can determine the probability of which stars are likely to be pre-main sequence or not. And similarly, theoretical isochrones may have issues in determining stellar ages, but now that we actually have a rather large sample of stars for which we know approximate ages from the populations in which they are found, we can use those ages to train a neural network to predict those ages for the individual pre-main sequence stars. And so with this in mind, we are able to create a catalog of all of the pre-main sequence stars that we have in the solar neighborhood. Here we have sources with a very large confidence level that these sources are indeed very young. We preferentially select sources from 0 to around 15 million years at this confidence threshold. If we were to lower the threshold a bit and allow a bit more contamination, we are able to go up to 40 million years to still have some contamination, but mostly avoid the binary sequence. And we are able to identify structures that we really never have really thought about as a community before, something that is a bit older, but we are able to see how all these populations have formed and evolved. And again, looking at everything in the 3D top-down, the sun is at the center, the galactic center is to the right. Plotting all of these sources in this top-down map reveals some sort of peculiar features. That we do have this ring of stars that is fully connected. And here we have SCO-Cenobi association, here we have Taurus, and they are connected via this older ring of stars that are still relatively young, still kind of within 30 to 40 million years. And then we have this outer ring of primate sequence stars that are all also suspiciously found on around the same distance from us. And it may seem weird why precisely you would have this ring of stars that is centered kind of in the vicinity of the sun. But the sun is actually found in a relatively special place in that we are found right in the middle of the local bubble, which is a cavity in the interstellar medium. And that's one of the reasons why we don't really have many primate sequence stars within 100 parsecs of us. And we can trace this local bubble using the diffuse interstellar bands, or we can look at it using dust opacity. And you can see where the local bubble ends. That's precisely where we have this inner ring of stars. So there probably has been something that have caused the local bubble, be it a supernova or some sort of other process. And it is very likely that this same process has influenced star formation within the solar neighborhood, in that the star formation had occurred preferentially kind of on the outer edges of this bubble. So to bring this talk to an end, while we cannot quite get to the point where we have ages for every single star that we have in the sky, we have significantly increased the census of the stars for which we can measure ages through various means. And we would be able to even further increase this catalog in the next decade through using rare chronology, through using X-ray activity and other methods. So to summarize, we have a very large catalog of stars with known ages. Young stars don't necessarily just form in clusters. They tend to form in these extended strings. And then they evolve further in time. And with these catalogs, we can have really just dig into and figure out a lot of things about how stars form and evolve, and not just stars, even how our own galaxy evolves as well. Thank you.
Okay, thank you, Marina, and thank you, Keivan, again. We're mostly out of time, but maybe we have time for a couple questions. So you can either type it into the chat or you can raise your hand. There's a question from Ida for Marina. She says, I think you mentioned this, but I missed it. What was your training set for the neural network to drive the stellar ages?
We've have one neural network for clusters that was trained for previously available ages for all the various clusters, and you can just feed in the photometry of the entire population and predict the ages. And then using this cluster catalog, we were able to take all of the structures younger than around 80 million years and impose some sort of color cuts to identify the primate sequence stars in that catalog. And then using that cluster catalog, we were able to train a neural network.
Okay. So I have a question, Marina. Can you go back to that figure of the stellar ages nearby? I mean, it was really striking to see all these stars at about 150 parsecs that all have almost the same age. I mean, is that, you described the structure, but it really is striking. Do we understand the age?
Yeah, so here, what is composed of the structure here? We have SCO-Cen. Here we have Taurus, somewhere over here. Here we have, it doesn't stand out on this map in particularly, but there is another population kind of over here, which is Castau, or it's centered on the young cluster Alpha Per. And we have also similar populations here near Vela. And so together they do form the string.
So I'm not very familiar with this. Was there thought to be a star forming event about, sorry, what's the age units here?
So the age ranges from just still forming stars to around 30 to 40 million years old.
So is it thought that there's a star forming event nearby about 40 million years ago?
It is possible, yes. Or there have been some, so looking at, going back to this map, you can see how this population is slightly above the galactic plane. This population is slightly below the galactic plane. This is referred to as the Gould's belt. And for decades, we have been wondering, well, what precisely has caused the Gould's belt to be so tilted relative to the galactic plane? And there have been various theories that there maybe have been a supernova, maybe there has been some sort of impact with the galactic plane that warped the disk locally. And we didn't really know about these older stars. We've known about a few, because we have known about Taurus, we have known about Orion, but not really much in between. And now pushing this census of stars for which we actually do have ages further and further down, we are able to see a more complete picture.
Okay, thanks. Are there, okay, one last question from Luke. He wants to know, it's a follow-up question on the same plot of the local bubble and the overdensity of 40 million year old stars. What fraction of nearby stars is this plot showing? About how much of an overdensity is it relative to the local field stars?
So this this is showing Gaia DR2 data that decreases in sensitivity beyond around a kiloparsec. With Gaia EDR3, you are able to push it out a little bit further, not with quite as high sensitivity because you don't have quite as many faint stars there. As to how much of an overdensity it is, so at around 90% confidence, you have I want to say on the order of 100,000 stars in comparison to many millions of field stars. So this, in the large scheme of things, it's not that significant. It's only because these stars are rather special and we can identify them easily that they stand out.
So maybe just follow up with the words order of magnitude. It's like a 1% or 0.1%.
Yeah, probably on the order of 0.1%, maybe less.
Got it. Thank you.
Okay, well, I think that wraps things up. Thank you, everybody, for coming. Thank you again, Marina and Keivan. And that's our last colloquium for the quarter. So happy holidays, everybody, and we'll see you all next year.
Thanks again, everyone.
Bye.
Great to see many old friends and colleagues. Take care. Thanks, Jim.
Yep, thank you. See you later.
All right, bye.